And thus we arrive at chapter 6 in our course, where all of our hard work of the previous chapters pays off. Now in this chapter, we will finally learn how to perform statistical tests, one of the most used and misused tools in statistics. In the first part, we will go through the entire reasoning underpinning this procedure, and thereby we will learn about the p-value and statistical significance. Afterwards, there will be a series of short lessons where in each lesson we will discuss a different statistical test. Now, before we start, I want to mention that all of the code for the first part will be discussed after this part is completely finished. The reason being that I don't want any interruptions because this train of thought is so crucial to this topic. And with this short introduction, let's get into the slides. Throughout this course, we worked really hard to understand the difference between sample data and population data. The sample being the data that is available to you, and the population being the underlying data about which you want to answer questions. Now we learned that when you compute statistics on your sample data, they will always be an approximation of the underlying population. And this of course introduces uncertainty. And it is this uncertainty that lies at the heart of statistics, namely getting population insights from sample analysis. Now in this chapter, we will finally bridge this gap between sample and population, and thereby it's worthwhile to get some more concrete insights that we want to learn on our population. And these will most often come in a form of questions. For instance, does my sample come from a normal distribution? Or how likely or unlikely is a specific observation given a certain assumption? Or the most common one, I have two samples, does the difference between these two samples translate to the underlying populations? Now these are the type of questions that we will be able to answer by using statistical testing. And one of the crucial parts of statistical testing, the concepts that make this entire framework work, are the p-value and statistical significance. And to learn about these new concepts, we will take an approach that by now has become very typical to this course. Instead of giving you an abstract definition up front, we will start out with an example and then use the knowledge and the tools that we learned throughout this course to get to these new insights in a very natural way. So let's start our journey into the p-value by looking at an example. And the scenario that we'll be looking at is to compare the savings rate between two neighboring communities. Now, for context, the savings rate is the percentage of income that a person is able to set aside each month. And we're asked to look at whether there is indeed a difference in this percentage between two neighboring communities. Now, the data that you are given, your data set, is survey data from 15 people for each community. So presumably they went out to each community and asked 15 people for their specific savings rate. And thus the challenge is the following. Given our sample data, 15 data points for each community, can we deduce some insights about the difference in savings rate about the underlying populations? Now the very natural initial step that you would do, of course, is to take your sample data and for each community compute the average savings rate of these 15 data points. And then compare these two averages and see whether they are indeed different or not. Now, chances are very large that they are indeed different. For each of your two sample sets, you will get a different average savings rate. But this is a sample statistic, and it will only be approximate for the underlying populations. So then, of course, the question arises, the difference between these two sample statistics, is this significant, meaning indicative for a difference in the two populations, or is it just by coincidence? And this is of course exactly the question that statistical testing tries to solve quantitatively. Let's make this now more concrete and consider that you indeed have two sample data sets, each containing 15 data points. If you compute the mean for sample 1, you get 1.206%. If you compute the mean for sample 2, you get 1.376%. And thus, the difference between these two is minus 0.17%. Or if you look proportion-wise, the difference is roughly 14%. Now you can see the datasets visualized here as a histogram, and the means are depicted as the vertical lines. And to reiterate, the question that we want to answer is whether this difference of 14% between the two sample means is indeed indicative for a difference in the population means. Now, to make progress in this question and to eventually get to the concept of the p-value, we again take a simulation mindset. Now, the first step in this is to look at the population distributions. Now, I know this is cheating because in reality, we do not have these underlying population distributions. We only have our sample sets. But for educational purposes, we can indeed look at these populations. In fact, I generated the concrete sample sets that we looked at in the previous slide from these two populations. Now, clearly, by looking at the population distributions, there is indeed a difference in savings rate between the two communities. In fact, the savings rate difference is 30%. The mean of population 1, which is the sky blue one, is 1. And the mean of population 2 I set to 1.3, so a difference of 30%. Now going back, this difference is not at all clear by looking at the sample histogram or even looking at the difference in means. And this again reflects the fact that a specific sample is just one of the many samples that one could possibly get from an underlying population. You can imagine in alternative universes that you would have gotten a different sample from these populations, or a different one, in fact many different ones. And each of these different samples would have gotten you not a difference of minus 0.17%, but an average difference of, let's say, 0.12, 0.26, 0.21, 0.18, or really any difference that you can think of, within boundaries of course. So each different sample would result in a new difference of means of sample statistics. Now, as we saw before, in fact in the chapter on the central limit theorem, where we did exactly this procedure, that all of these sample statistics, these differences in means, they will form themselves a distribution. But unfortunately, of course, in the same way that the population histograms are in reality unavailable to us, these different samples are in reality also unavailable to us. We're only given one sample data set. So therefore, this distribution of the differences of sample means is also unavailable to us. Except of course that mathematicians are very hardworking people. And indeed, they have developed a distribution of these sample statistics. In our specific example, a distribution of the differences of means of all our different possible samples. Now, there is one caveat. We have available to us this distribution, but only under a specific assumption, namely the null hypothesis. Now, what is the null hypothesis? This is the assumption that the underlying populations do not have a difference in the specific statistic that we are looking at. So in our example, where we are investigating whether there is a difference in mean between the two populations, the null hypothesis would be that there is no difference in mean and that the average savings rate for both populations are exactly equal. So that is the null hypothesis. Basically, nothing interesting happens. So under this assumption, we have available to us the distribution of the sample statistics. And this distribution looks a lot like the normal distribution, and it's depicted here. In fact, for large sample sizes, this is a normal distribution. But for low sample sizes, for instance, in our case, for 15 samples, this is a student t distribution. And it looks like a normal distribution, it just has much longer tails. Now you might be surprised that in fact you generated this exact distribution of sample means before in this course. In particular, in chapter 4. If we go back briefly to the figures that we generated in chapter 4, then we did the following. On the first row here, we have two populations, and they are exactly equal. They have the same mean, centered around 1. They have the same variance, and they are both normal distributions. Now, if we generate samples from these distributions and we compute the mean, then as we just saw again, these means will form a distribution on their own. And the central limit theorem says that these distributions of means will also be normal distributions. And they are also identical between the two samples. Here it is centered around 1, the population mean, and it goes roughly from 0.6 to 1.4. And the same is true for sample 2. All of these sample means will be centered around 1 and go from 0.6 to 1.4. And now to generate the distribution that we have in our slides at this point, we can take the difference between the sample means for each sample that we generate. And then these differences can of course also be visualized as a histogram. And that is exactly this histogram. And we indeed see that the differences of sample means also follow this normal distribution. And this is how you actually generated this distribution yourself already in chapter 4. And the fact that we now have this distribution to our disposal is crucial to the entire reasoning underpinning statistical testing. Now we have two ingredients. The first one being the specific value that we got by calculating the difference in means of our two specific sample datasets. And the second ingredient is this distribution of possible differences in means if the underlying populations do not show a difference in means, the null hypothesis. And thus, what we can now do is to compare our specific sample value with the possible values contained in this distribution under the null hypothesis. And visually, we can do this by simply drawing our value on this histogram. In this case, we draw it right here, being the minus 0.17% difference. And then in the next step, we can use our knowledge on distributions, percentiles, and data intervals to draw some conclusions from this comparison. In fact, there can be two scenarios. The first scenario is that the null hypothesis is indeed correct, namely that there is no difference in means of the underlying populations of our sample datasets. Now, this means in turn that the distribution here is indeed the correct distribution. And if this is the case, that our sample statistic should be in line with this distribution. This means no extreme values, but it should be somewhere in the bulk of this histogram. And then we can conclude that our specific sample statistic that we computed indicates that there is in fact no difference in the population means. And thus this would conclude that there is no difference in savings rate between the two communities. So that is scenario number 1. The second scenario deals with the case where the value of our specific sample statistic is extreme compared to this underlying distribution, meaning that our value falls at the edges of this histogram. Now, because our sample statistic is an extreme value, the underlying distribution that we compare it with is unlikely to be the right one, simply because of the fact that it is unlikely to observe extreme values. Now, because this distribution is unlikely to be the right one, it means that its underlying assumptions might be wrong. Now remember, the underlying assumption is the null hypothesis, meaning that there is no meaningful difference between the underlying populations. Now this in turn means that the specific sample from which we calculated our extreme sample statistic is unlikely to have been drawn from populations that have the same mean. And thus we can conclude that the difference in mean that we computed from our specific sample are indicative of a difference in mean of the underlying populations, exactly what we were asked to figure out. And it is this reasoning that underpins all of statistical testing. So if you understand this reasoning, then you understand statistical testing. So in a nutshell, the first step is that you compute your sample statistic from the samples that you are given. Then you compare this value of your sample statistic to a distribution that is true under the null hypothesis, meaning that there is nothing going on with the underlying populations. Now, if your value lies within the bulk of this distribution, then there is indeed nothing going on with the underlying populations. If, on the other hand, this value is extreme compared to the underlying distribution, then that means that this distribution is unlikely to be right, meaning that the null hypothesis is likely to be wrong, which in turn means that the underlying populations are likely to be different. And thus, you can conclude that the sample statistic of your specific sample is indicative for the underlying population statistics, which is what you set out to prove. And at this point, of course, it is time to get some numbers involved into this story. For instance, you might raise a question: how extreme is extreme enough to reject the null hypothesis? Well, that is of course what we will learn in the next lesson, which will bring us to the p-value.